Right, they are exact. So precisely, I mean, the chain rule says that a maximum, you're right. Since distance is positive, the square of the distance will be maximized wherever the distance is maximized, essentially by the chain rule applied to distance squared. Distance squared differentiates to 2 times distance yes. So why can't I do that for these, you know? And yet, sometimes people write down square roots and do things with square root. There must be some reason to not get rid of the square root.
Maybe it's people just like stringing together equations rather than splitting it into separate. You're like, now we would consider the square.
Maybe. So here is this is the metric, okay? The metric, I have basically just, take this expression we derived, multiply by dt squared formally, and that gives you ds squared is dr squared plus r. Now I'm using ds as the arc length. Sorry. Dr squared plus r squared d theta squared plus dz squared. There's the metric in polar coordinates. This is the metric in cylindrical coordinates. The metric in spherical coordinates is this guy. Now, by metric, I mean the infinitesimal arc length squared. That's a heuristic, right? But this kind of gives you a template for constructing arc length integrals, right? If you freeze, for example, if you want to define the arc length on a sphere, you could freeze dr and then minimize this thing, right? Integrating over. And then probably smarter still, decide to make theta a function of phi or phi a function of theta. Then you can rewrite this as, what I'm trying to say is, how to say this? So ds squared, let's suppose that we're working on a sphere. So we'd have r squared sine squared theta d phi squared plus r squared d theta squared. I love parametric equations, but sometimes it pays off to operate a little differently. And like here, this could also be rewritten as r squared sine squared theta plus r squared d theta d phi quantity squared, right? All of that times d phi squared. So you could set up your you could set up your j theta, all right, with your dependent variable being phi, so to speak, independent variable being phi, dependent variable being theta, excuse me, and you do the integral, here I'll put the square root in just for kicks, r squared sine squared theta plus, I forgot to, r squared, I guess I'd like to say theta dot squared, but I guess I should say, I don't know what the best notation here is, theta prime squared. I usually try to reserve the dot for time, so fine. D phi. So to find geodesics on the sphere, I could look at the other Lagrange equations which come from this. If this thing is, L, I'd look at partial L, partial phi equals to dd phi, right, of partial L, partial theta prime. And solutions to that equation should give me geodesics on spheres. And you see, if you're not interested in parametric equations for the geodesics, then this is a better approach because you just get relations between the angles on the sphere, and that might, I don't know. I'm not sure which is better. I always get stuck on this problem. I know the answers. They're great circles, right? But how do you actually derive that? Well, you can solve this and do that. All right. Maybe I made that a homework I'll try to fix this for your homework. It's actually a very nice problem that's not that hard. If I set it up in the right way, instead of getting the time, you actually, I mean, I should fix points like from, say, theta naught, comma z naught to theta 1, z1. Then we actually have endpoints, and it actually fits the thing we were doing, and we're not being fuzzy. I don't know what this really means, right? I haven't explained that. Yeah, I did it this way in the notes too, didn't I? Oh well. Fine. Whatever. Okay, so physics. Let's talk about physics some more. I know you guys like physics, right? Come on, you gotta love physics. Physics loves you. I don't know, maybe it doesn't, I don't know. I'm not sure I know physics anymore. But anyway, so long story short, this is Newton's equation, right? Newton's second law, ma equals to f. We can rewrite this as being to the time rate change of momentum being f, right? One thing, we can do that. Of course, we could also take Newton's second law and rewrite it as mx double dot, my double dot, mz double dot is equal to the x, z, y, and z components of the net force, respectively, right? Now, so first of all, one of the things you might notice is that if you rewrite this as differential equations, you've got, the time derivative of the x momentum, y momentum, z momentum is respectively the x, y, z force components, respectively. May or may not have thought about this, but if in terms of momentum, Newton's second law becomes a system of first-order differential equations, right? This is kind of reduction of order in some sense. So the Lagrangian, come on. So here's how we construct the Lagrangian in physics. In physics, when I say Lagrangian, it's not some sort of, like I've been using the term Lagrangian in here as sort of a grab bag for it's whatever we're integrating our functional for, right? It's the thing we're integrating in the functional. But Lagrangian in physics has a more fixed and technical meaning. It is the thing it's the thing you integrate to get the action. But more specifically, it's just kinetic energy minus potential energy for the system. T minus U is, often we use T in physics for kinetic energy and U for potential. If F is conservative, then it's minus the gradient of a potential energy function, right? And so we'd like to have, I mean, we know that we prove in physics that energy is conserved, right? T plus U is a conserved quantity. So let's see here. I'm claiming that the Lagrangian should be T minus U. Let's see why that makes sense. Okay? And it also, there's more that happens here. It's really neat. So this is the Lagrangian for three dimensions. And here you have a potential energy function, which is a function of y, x, and z. Here's my kinetic energy, right? So the Lagrange equations, three variables, right? Three dependent variables. I get three sets of equations, one for x, one for y, one for z. This is mx dot dot. This is my dot dot, mz dot dot. As we've seen already, partial L partial x is got nothing to do with this, and it's just the x derivative of that with a minus, but by definition, that is the x component of the conservative force we're looking at. So this is exactly the x component of Newton's second law. This is exactly the y component of Newton's second law. This is exactly the z component of Newton's second law. What could be simpler? But here's where it gets interesting. Newton's law, right, F equals ma, assumes a rectilinear coordinate system. The Euler-Lagrange equations make no such assumption. Euler-Lagrange equations we can write for curved linear coordinates. We can write the equations of motion for a ball rolling on a sphere or something, just the same. It's amazing what you can do with it. Excuse me. So in a nutshell, Hamilton's principle says you take that Lagrangian I just showed you, and you minimize the action, that gives you the laws of physics for physical trajectories. This is Hamilton's principle. See if I have an example here that's, easy physics example. Projectile motion. Here's the Lagrangian. Kinetic energy minus mgz, because mgz is potential energy due to gravity near the surface of the Earth. So, yep, you get mx double dot is 0, my double dot is 0, mz double dot is minus mg. Integrate those things. There's your favorite kinematic formulas from Physics 231. Derived in a way which should never be shown in Physics 231. But I think I might have once. I think I might have shown Physics 231 this once upon a time. It was a simpler time. Simple pendulum. So this probably requires a picture. Let's see here. Length L, right? They measured off the vertical, so theta is like this. So here's my mass m, right? So with that system of coordinates, minus mgl cosine theta is h, because I'm saying that potential energy is 0 right here. So negative potential energy down here, basically z is equal to minus mgl cosine theta, which you can see in this picture. But Lagrangian is t minus u, so that minus cancels the minus and gives you plus mgl cosine theta. And so the Lagrange equations say this. There's only one, right? And so that is ml squared theta dot equal to minus mgl sine theta. Cancel the ml's, and you get this impossible to solve second order differential equation, which we can solve for small angles to give us simple harmonic motion, simple pendulum. But of course that's an approximation, because that's not really linear, far from it. I don't think this does the full justice to it, though. I mean, I've got, this is the example I have in the notes, but let me show you guys an example of what you can do with this stuff. So I want you to appreciate this method for what it is. Let's just, I think this should be a relatively simple exercise. What do Newton's equations look like for a free particle in spherical coordinates? That's a maddeningly complicated question without the techniques we have at our disposal today. You know what I'm asking you? What are the, so you have a particle, right? It's free. Free particle, not three, free particle in 3 dimensions. What are Newton's equations in spherical coordinates? We know what Newton's equations are in rectilinear coordinates, right? But my question is, what are the corresponding equations in r, theta, and phi? So I just erased it. Come on. So the Lagrangian is m over 2. Dang it. Man. When I was a physics major, once upon a time, I had these things memorized. Like, I just knew them because I derived them so many times. I need to teach physics here, but unfortunately, teaching physics here will not fix this for me for some reason. By the way, our introduction to the term metric today was very hand-wavy and heuristic. We will come back to this metric thing and talk about it much more precisely in the totality of this course, don't worry. That was not the end of the metric, just the beginning. Okay, so m over 2 r dot squared plus, and this r would be your usual rho, right? So I'm thinking I'm using physics coordinate here. My theta and my phi might well be reversed. There you go. I think this is physics coordinates, which is this is rho is going to r, theta is going to phi, and phi is going to theta, I think. Most likely, okay? In other words, if you wish me to be a good citizen of the math department, I will fix it for us. This is m rho squared plus rho squared sine squared phi, theta dot squared, right? Plus rho squared phi dot squared. Feel better? You're like, that's better. Okay, great. So here we go. Partial L, partial rho is equal to d dt, partial L, partial rho dot. What's that? Oh, that's something. It's two things. It's 2 rho sine squared phi, right? Theta dot squared plus 2 rho phi dot squared equals to, now this one's easier, m rho double dot. Oh. Excuse me. Oh. That'll teach. Hidden cost for Travis. Let's see here. Partial L. Partial theta. ddt. Partial L, partial theta dot. Partial L, partial theta is 0. Yay. On the other hand, theta dot is what? Oh, yeah, should I put my m in? Should I put the m's back up here? I don't know. I gotta make a choice, don't I? Choices are hard. Rho squared, sine squared phi. I'm gonna cancel the 2 and the m over 2. And that's just going to be theta double. Theta dot? No, theta dot, right? Yeah. It's less controversial. I mean, that's just algebra. There's a 2, there's a 2, and there's an m over 2. So, and there's an m over here. So, do I lose the ddt? Oh, shame on me. That's more serious problem. Thank you. You're right. I should have ddt. Oh, but I got this double dot. Here, I'll leave it ugly. M. Right? Then partial L, partial phi, ddt, partial L, partial phi dot. That gives me, that turns this m over 2, fine, m over 2 rho squared. 2 sine phi, cosine phi, theta dot squared. Please, okay, thankfully that's the only place where there's phi dependence. And that's equal to ddt of what? Of partial L partial phi dot, which thankfully is just what? M over 2 times rho squared times 2 phi dot, right? These are Newton's equations for a free particle in spherical coordinates. You could solve these in principle for like rho double dot, for theta double dot, for phi double dot, and see like all these sort of fictitious forces appearing because you're not working in straight line coordinates. You could do other things, like you could suppose that you're going to study the motion of a particle constrained to a sphere. So that just puts rho dot equal to 0. There's a method of Lagrange multipliers for here. If you want to throw in a Lagrange multiplier, how you do it is like this. You do plus lambda times your constraint. And then your Euler-Lagrange equations for the constraint variable lambda, there is none of this, and this is just constraint equals to 0. You can build constraints into Lagrangians by just adding them, and they're treated on the same footing as the dynamical variables. There are many more things you can do. It really should be a course that we force math majors to take, honestly. I guess you can only live one life. You only have time for so much. This turns into a whole course. What I'm showing you is very physicsy. Mathematicians worry about other things, like what about a second derivative test? And what about actually proving these things I said over here? These all have names that I have forgotten. Like this is the fact that you can look at this for all eta and get that this is 0. That's somebody's theorem. I forget the somebody, but when I was first preparing this chapter, I read a bunch of variational calculus books and trying to get more history and so forth. And as far as I can tell, the math books have tons and tons of theory, but no better examples than I learned in physics. Yeah. Oh, before I forget, one other thing, guys. So generically speaking, if you have L, which is a function of Q, Qi and Qi dot and X, I suppose. The interesting thing is partial L, partial Qi dot is the ith momentum. Like a great example of this is in the plane, we'd have m over 2, right? R squared theta dot squared, right? Plus r squared, r dot squared. This would be the free particle Lagrangian in polar coordinates. If you calculate partial L, partial theta dot, this will give us what? Well, I'll do the easy one. Partial L, partial r dot, what's that? It's mr dot, right? This is the so-called radial momentum, p sub r. Partial L, partial theta dot gives you m r squared theta dot, which you might recognize if I wrote it instead as the moment of inertia times omega. This is the moment of inertia for a point particle. This is the angular velocity. This is angular momentum. So for an arbitrary Lagrangian, you want to calculate the momentum of the ith coordinate, simple partial derivative with respect to the ith coordinate. That produces the generalized momentum with respect to that coordinate. See, Lagrangians can't tell the difference between curves and lines. They're just coordinates, and it treats them all on an equal footing, radial, linear, circular, whatever. So you can understand why physics majors have to learn variational calculus, because it allows you to solve so many problems that we can't even state in terms of physics 231 terminology. Not really. Oh, also, this is how modern physics is stated. Modern physics is based on energy principles. Conservation of energy is central. So when you go on, you learn classical field theories. There's Lagrange densities. At the base of quantum field theory, there's these classical functionals, which are all written in terms of integrals of fields over jet spaces and so forth. And it's all Euler-Lagrange equations at the base of it all. That's the general idea, Euler-Lagrange equations. But anyway. So I think my advisor, probably a lot of his life's work has been in like technical theorems involving Euler-Lagrange equations, one or another. I had an undergraduate course that was called Special Topics in the Euler-Lagrange equation. So it was like Math 798 at NC State. It was great. It was so much fun. It's really good. I wish we could do those sorts of things here. I mean, this is the closest. I mean, I misbehave. If you're here and you do homework, I'm going to pass you. Like, it's almost guaranteed. You'd have to really, really offend me to do otherwise in here. Oh, I should have to edit this out, right? No, spread the word. Why doesn't more people take this, right?
They're already terrified of you?
They're already terrified. I am harmless. I'm a harmless, lovable fuzzball. I haven't failed that many students. I don't think so. You can hit it. I think adjusted for Kang time, we're